Does stress analysis differ between metals and composites? Have you ever wondered how stress analysis changes when comparing metals to composite materials? This question is crucial for anyone involved in mechanical engineering. Let's break it down. First, metals and composites behave quite differently under stress. Metals are generally isotropic, meaning their properties are consistent in all directions. This allows engineers to use classical methods like von Mises stress criteria and linear elasticity for analysis. On the other hand, composites are often anisotropic or orthotropic. This means their properties vary based on the direction of the applied load. Composites consist of multiple layers, or plies, with fibers oriented in different directions. When looking at material behavior, metals tend to deform plastically after yielding. This means they can change shape without breaking, and their stress-strain relationships often include plasticity and isotropic hardening. Composites, however, fail differently. They do not yield like metals. Instead, they can experience fiber breakage, matrix cracking, or delamination. This makes stress analysis for composites more complex, as engineers must predict these various failure modes. Next, consider how stress is distributed through the thickness of the materials. In metals, this distribution is usually continuous. But in composites, stress can be discontinuous between plies due to differences in stiffness and orientation. This can lead to interlaminar shear stresses, which may cause delamination. Now, let's talk about the types of stress components involved. Metals mainly requiring analysis of normal and shear stresses. In contrast, composites requiring additional attention to interlaminar shear stresses and stresses specific to each ply, both along the fiber direction and in the transverse direction. The methods used for analysis also differ. For metals, engineers often relying on classical elasticity and plasticity theories. For composites, laminate theory is employed, which considers each ply's stiffness matrix and orientation. This often requires more advanced numerical methods, such as finite element analysis, to achieve ply-level resolution. When it comes to input data and failure criteria, metals typically use yield strength, ultimate tensile strength, and von Mises stress for predictions. Composites, however, need unidirectional strength and stiffness data for each ply, along with failure criteria like Tsaiwu or Hashin tailored to their behavior. In practical applications, stress analysis for composites is vital in industries like aerospace and mechanical engineering. These materials are often used to design lightweight, high-strength structures where traditional metal analysis methods may fall short. For example, when designing composite joints, such as bolted or bonded joints, specialized stress analysis is necessary to predict load transfer and avoid premature failure. Software tools for composite stress analysis can plot stresses in each ply, helping engineers identify critical layers and potential delamination zones. This level of detail is not typically necessary for metals. In summary, stress analysis for metals and composites involves different approaches due to their distinct mechanical behaviors and structural characteristics. Understanding these differences is essential for engineers working with these materials.